Okay, so I think we can start. And welcome back, or welcome for the new ones, to the third day of QubiTO Quantum Days. And I hope you're enjoying this journey, let's say. And in the past 2 days, we had a more like theoretical point of view. And today, we will have a more hands-on experience, so something more practical. And you will try to like program a real quantum computer. And so for this event, we have our guest, and I'll let you.
Okay, so as Leonardo said, I'm always Mark, by the way. Yeah, so we can present ourselves. A couple of days ago, we started with the history of quantum mechanics. We start with Professor Riccardo Adami. Yesterday, we had the great contribution of Professor Aronson, which took us from the history, from the capabilities up to the actual implementations of quantum computing and its limits, which were very interesting. And today we get to the heart of the subject, to what we do and what we use on a weekly basis, basically. As you may have seen from the news, have heard from friends of friends, the Politecnico of Torino University bought a quantum computer from IQM, which is a producer of quantum computers based on superconducting technology. And last May, it started its mounting, and from this year, we finally had the opportunity to use it. And we thought that it might have been a great opportunity for the majority of the population of the Politecnico, and also any guest who has registered in the event, to use a quantum computer maybe for the first time ever. So we decided to invite a researcher that is responsible for laboratories of a subject that we follow, of quantum computing, with Professor Bartolomeo Montrucchio, who you knew on the first day. And he's going to take us through a bit of an explanation of how this quantum computer works, and why did the Politecnico choose to buy it, and what are its implications, what we can do with it, why it's useful for the entire population of Politecnico di Torino. So I'd say that without further ado, we can start this workshop on the Lagrange quantum computer. So please welcome Dr. Emanuele Dri.
Thank you. Thank you. Yes, I'm Emanuele Dri. I'm a researcher at Links Foundation. Links Foundation is a research foundation, a non-profit, whose aim is to being a bridge between university and industries, or let's say practical application of what we research here. So essentially, we strictly collaborate with the Politecnico. Actually, we are hosted here in Politecnico, and we collaborate also for the courses of the master degree in quantum engineering. And as your colleague said, I'm responsible for the labs in the quantum computing course. Okay, so today, interestingly, we'll run experiments on a quantum computer, on a real quantum computer. The quantum computer here is also here in Politecnico, in the ex-Sala Vax, the former Sala Vax. And if you want to follow along and run the experiment on the quantum computer, you can do so. You just need to scan the QR code that you see on the screen, or alternatively, you can also go to the URL, so tinyurl.com/QubiTO. Both approaches will bring you to the notebook, the Colab notebook that I'm using. And just before I start, a brief introduction about Colab. So Google Colab is a tool that allows you to write and execute Python in your browser, okay? So no matter what your PC specs are, if you are able to connect to the internet and use a regular browser, you will be able to follow along with this session, okay? So the benefits are that there is zero configuration required, that you can access GPUs free of charge, but this is not of interest for us today. Moreover, you can easily share your code, and this is what I'm doing with you today, okay? The idea is that you have two types of cell. The first one are these markdown cell, where you have text or other similar items. And then you have code cells, like this one, okay? Essentially here, you can click And if you have a Google account, the other ingredient, you can execute essentially the notebook, okay? So now, since it is a requirement, as I told you, I suggest you to log in into Google. I should have done this before, but give me a second. And let's retrieve the password, of course. The idea is that then you will be able to run the code and follow along the session. First, maybe while I do this, the only thing I wanted to share also with you is that indeed we'll be using the quantum computer here at Politecnico, which is a 5-qubit quantum computer produced by IQM in Finland, and essentially is, let's say, at our disposal thanks to a collaboration between Fondazione Links, Politecnico di Torino, and INRIM, which is the National Institute of Metrology, the Italian National Institute of Metrology. So the quantum computer appears like this, okay? So the main thing is the one on the left, which is the whole infrastructure of the quantum computer. And essentially, 90% of what you see in the left picture is a very advanced cryostat, okay? So it's required to cool down the quantum processing unit, which is the proper and real quantum computer, down to tens of millikelvins, okay? Which is an extremely low temperature, very close to absolute zero, and is colder than outer space. So in principle, inside the white cylinder at the center of the left image, you have this chandelier, which probably you already saw in some other images online or in videos. And at the bottom of this chandelier, you have again the quantum processing unit, where the qubits reside. Okay? This object needs to be cooled down to around 20 millikelvin. It can be said that is one of the coldest places in the whole universe. Okay? So the idea here is that the first thing we want to do is understand how we program a quantum computer. In order to understand that, I need to recover some concepts that maybe were already explained in past sessions, but still is useful to give a recap. Specifically, the difference between the classical bit, which is the traditional unit of information in classical computation, and the qubit, which is instead is the quantum counterpart of the classical bit. While the classical bit can be in one of two defined states, okay, 0 or 1, and also we can think of it using an analogy, as any analogy, of course, is good up to a certain point, but please follow me. You can think of it as a light switch that is either on or off, okay? 1 or 0. Instead, the qubit is something more complex, still can be in the 0 or 1 state, but crucially, the qubit can also be in a superposition of 0 and 1. What does this mean? It means that it can exist as a combination of both states with certain probabilities, okay? If you want to keep up with the analogy of the light switch, again, this is not completely correct, but gives you the idea. You can think about a light dimmer, okay, instead of a switch. And so it can be fully off, fully on, but also anywhere in between, okay? Importantly, when a qubit is measured, so when we want to observe our qubit to know the result of our computation, the qubit collapses into a definite classical state, which is always 0 or 1. So this superposition can exist only during the computation, but at the end of the computation, once I measure the qubits, I observe the qubits, they will collapse to 0 or 1, okay? Which are the same state of the classical bit. Another important thing is the notation we'll use. We won't need a lot of notation for this notebook, for this simple example, but a very small amount is always good and allow you to have the tools to navigate more complex algorithms. So to describe the states of the qubits, quantum mechanics uses a special mathematical notation that's called Dirac notation, okay? It's a let's say, fancy notation that you use to represent essentially vectors and matrices, etc. So specifically, the cat notation, and you see the symbol here, this is pronounced cat psi, okay, represent a quantum state vector. You can think of it as a column vector. In fact, it is a column vector. In this case, cat 0 represents the quantum state corresponding to the classical bit 0. So the column vector will be the one you see on the notebook. Cat 1 represents the quantum state corresponding to the classical bit 1. So the column vector is instead this one, okay? How can we represent the superposition phenomenon? So the fact that a qubit during the computation can be in a superposition of 0 and 1. Well, we use a linear combination of the two basis states, cat 0 and cat 1, as you see on the slide. So cat psi, in this case, is a generic superposition of the two basis states, cat 0 and cat 1. Okay? So it represents one qubit in this superposition. Here, alpha and beta are complex numbers, and they are called probability amplitudes. Why they are called probability amplitudes? Because they tell us the probability of measuring the qubit as 0 or 1. In particular, the probability of measuring 0 is the modulo squared of alpha, and the probability of measuring 1 is the modulo squared of beta. Importantly, the modulo squared of alpha plus the modulo squared of beta, of course, must be equal to 1, since we are dealing with probabilities. The Dirac notation is powerful and is also useful because it allows us to compactly represent and manipulate quantum states and operation in quantum computing. Okay, so this is the reason why we use this notation. You'll see that it's quite convenient when we have to manipulate quantum objects. Now, these were all markdown cells. Okay, so text, images, all fine. But now I think it's time to start with some code. So the first thing I want you to do is running this code cell, okay, clicking on the button here. And this cell is doing two things. It's installing some libraries that we'll need, okay? Specifically, is installing the IQM client library, which is a Python library that we use to access and interact with the quantum computer. Our quantum computer is produced by IQM, is an IQM Spark machine that we called Lagrange here in Turin. And essentially, this library allows you to interact with the quantum computer using Python, and specifically using the Qiskit library. Maybe you already heard about the Qiskit library. It's an open source quantum software development kit, initially developed by IBM, but actually, again, is open source, and is useful if you want to program quantum algorithms. Then we have some libraries that actually are only used to have a nicer visualization, a nice visualization of our circuit, our quantum circuits, which is, again, the model that we use to represent our quantum algorithms. And in particular, we have matplotlib and pylatex. Finally, the other thing this cell is doing is installing Lagrange client. Lagrange client was developed by one of my colleagues at Fondazione Links, and is a script that you can use to retrieve the token that you need to access the machine. Because of course, it's not like everybody can access the machine freely. You need to have an authentication token. And the way to get the authentication token, there are two main ways, okay? The first way is if you have a Polito account and you registered for the event, you will be able to use the credential of your Polito account, so your institutional account for Politecnico di Torino, to get a token. And this is very nice, very convenient also for students during courses. If you don't have a Polito account, or you did not use your Polito account to register for this event, you will still be able to follow along, because for this special occasion, in the notebook, there will be also provided a token that you can use, and that will be valid only for today. Essentially, the token is produced using my credentials, but you will be able to use it to run on the quantum computer. Okay? So again, the only thing you need to do is connect to the runtime. The environment is already prepared by Google, and the additional library we need are obtained just clicking on the run button. Okay. Now, what we want to do after you have installed, maybe I will leave you a couple of minutes so that everyone can do this first step. And if anybody still needs to scan the QR code to access the notebook, here it is. And I will.
Say that if you need some help, you can ask also the people with the purple shirt to help with the thing.
Okay. So you should see something like what you'll see now is connecting to the environment and then is simply executing the cell and installing the required libraries. Okay. Then the next step is to prepare our quantum circuit to be executed. Okay. We consider this the hello world example in quantum computing because it's a very straightforward example, but I think it's suitable for, let's say, the plethora of different backgrounds that are probably in this room today. And of course, this will equip you with the knowledge to run, if you want, more complex quantum circuits in the future. Okay. So this example is tailored to show and experiment with quantum entanglement. Quantum entanglement is a phenomenon where two or more particles become linked in such a way that the quantum state of each particle cannot be described independently of the others. Okay, so is a sort of very strong correlation, although correlation is not maybe the correct term, but you can imagine it as a very strong correlation. And even if these particles are then separated by large distances, this relation still remains. Okay. So when one of the entangled particle is measured, the state of the other is instantaneously determined. Okay. So essentially, if I collapse one of the qubits in a pair of two entangled qubits, the state of the second qubit is also immediately determined without being any more probabilistic. This correlation is stronger than any classical correlation and is a cornerstone of quantum mechanics. Together with the other phenomenon we described of superposition of states, entanglement is another of the cornerstone of quantum mechanics. Now, the Bell states are example of this phenomenon of entanglement. Specifically, they are a set of 4 maximally entangled 2-qubit states. We'll see the most famous one. And in this case, it's the phi plus state. Okay? Let's see at the description of the state. Let's look at the description. So essentially, is a superposition of 2 possible configurations that you could observe and measure in the output. The first one is 0, 0, which means that both the qubits in this 2-qubit pair are measured in the 0 state. The second possible configuration is 1, 1, which means that both the qubits are measured in the 1 state. So we are restricting the possible outputs to cases in which both qubits are in the same state. There is no possibility preparing this state of observing one qubit in the 0 state and the other one in the 1 state, or vice versa. This is not possible. In fact, if you check the probability amplitude, which is 1 over square root of 2 for both of these configurations, and if you take the modulo squared, you get that the probability is 50% of observing 0, 0 and 50% of observing 1, 1. There are no other possibilities, which means that if I just measure one of the 2 qubits, I already know the state that I will observe once I measure the other qubit. Okay? If I measure 0 in one of the qubits and the other one, I don't look at it. Still, I already know if the state is this one, that once I measure the second one, it will be also 0. How can we prepare this state using Qiskit? So the quantum software development kit that I described before. Well, we need several things. They are all explained. Please notice that all the lines in this cell of code are explained in the markdown below. Okay, so if something is not clear for my explanation, you have the reference of for each line of what is doing what. Okay, but basically, we need to import a class from Qiskit, which is called quantum circuit, and an instance of this class will represent one specific quantum circuit. To create the instance, we specify how many qubits we want in our quantum circuit. In this case, we want 2 qubits, okay? Because we have the 2-qubit pair for the Bell state. Then what we do is we use this method .h to apply what's called an Hadamard gate on the qubit with index 0. Okay, if you look here, it's also explained. This is applying an Hadamard gate to the first qubit, qubit number 0, and the Hadamard gate, or H gate, is a fundamental operation in quantum computing. Imagine our first qubit start as a 0. By convention in Qiskit, all qubits start as 0. The Hadamard gate puts the qubit into a superposition state. This means it's now both 0 and 1 simultaneously with equal probability until we measure it. It means that this gate is putting qubit 0 in this superposition where we expect, if we measure it multiple times, to observe half of the times 0 and half of the times 1. Okay? This is on qubit 0. Then we are doing something more. We are applying another gate. The gates are the way we operate on qubits. Essentially, each gate represents a unitary operation that can be represented using a unitary matrix. But in this case, you see also the gates displayed as these little blocks and drawings on the circuit. The circuit is structured in a way that allows us to see the time on the horizontal axis, and each wire instead on the vertical axis represents 1 qubit. Okay, so Q0 is 1 qubit, Q1 is another qubit, and this other object you see on the bottom is the register with the classical bits on which we store the measurement of the qubits. So we're applying again the Hadamard on qubit 0. We are applying what's called a CNOT gate or a controlled NOT gate on qubit 1. But be careful because the control NOT gate is a specific object that is related to entanglement. In fact, if you look at the description, what it does is that it sets a control qubit, which in this case will be qubit 0, and a target qubit, which will be qubit 1. And if the control qubit, so qubit 0 in this case, is 1, then the gate flips the state of the target qubit. Okay, so let's say, for example, the first qubit, the top qubit, is 1, and the second qubit, the bottom qubit, is 0. If the first qubit is 1, the control condition is satisfied. So indeed, this gate will apply a NOT gate on qubit 1. Assuming qubit 1 starts in the 0 state, it means that this put qubit 1 in the 1 state. Okay, we are flipping the state. Of course, if qubit 0 is in the 0 state, nothing happens. This gate is not applied. The application of this NOT gate is conditioned on the state of the control qubit. This established that relationship between the two qubits that allow us to create entanglement. At an implementation level, all these gates that may seem abstract objects right now, in our quantum computer, are microwave pulses. Are microwave pulses that are sent through specific channels to the qubits, and then once we want to obtain the output from the circuit, we measure and we get a shift in some characteristic frequency of some resonators inside the QPU, and we interpret that as output. We are a layer of abstraction above these physical processes, and in fact, we don't see this kind of input-output phenomenon, but still, under the hood, this is what's happening, okay? But on a higher level, we are just putting these objects, this gate provided by Qiskit, and we will compile this circuit in order to traduce these gates into, these gates into microwave pulses. Okay, so the last step again is to measure the qubits, okay? Measure all, just saying to the circuit, I want to measure both my qubits and store the result of these measurements. Again, once I measure, I can only see 0 or 1 for each of the qubits on some classical bits of information. This is all explained here. Now, if this is somewhat clear, okay, at a practical level, you just need, again, to click on the cell and it will generate the circuit. The draw method is just drawing this kind of representation using matplotlib. If this is clear, the next step would be to execute this circuit, okay? So this circuit is preparing the bell state that we described before. So what we would like to see from executing this circuit on the quantum computer is to observe only situation in which both the qubits are in the same state. So either 0, 0 or 1, 1. How can we make sure that this is the case? We run experiments on our quantum computer multiple times because quantum computing is intrinsically a probabilistic computational model, okay? It's not deterministic, and it means that in order to reconstruct the output distribution, we need to execute the experiment, so in this case, the quantum circuit, multiple times. Each of these time is called a shot, and so we repeat the circuit execution for a certain amount of shots that we can specify as a parameter when we launch the job on the quantum computer. So now, before we go on and execute on the quantum computer, I want to highlight that here you have a link. If you click on the link and you allow Colab to redirect you to the page, you land on the page of the documentation of our quantum computer. This is maintained by us at Fondazione Links, and essentially you have some information on the quantum computer itself. You have the status of the machine, which luckily is up as of now. We have information on the architecture and many, many details also on how we implemented the platform that controls the access to the quantum machine. You have some details about how can we use the machine, but we'll see together this in the notebook. And you have also, this is really interesting, some information about the dashboard. Of course, there are no active jobs at the moment, but what I want you to show are these links where you can see metrics related to the calibration of the machine. So the quality of the gates we can perform on the machine, for example, and other parameters that are specific to the quantum computer. And also a cryostat dashboard in which you can check, for example, the current temperature of the quantum processing unit. So this is in real time. As of now, again, we are around 20 millikelvin. Okay, you can check this by yourself. And there are many other information. If you want details on those, I can provide you with a list. But still, yeah. Yes. Yes. There is a question. For cells in step 2 are hidden. Can you open them for us to see in our computer too? Not sure I get the question. What's hidden in step 2? I think this is everything that there is to see. By the way, if you want, you can create a copy of this notebook. You can hide or show any cell you want. But as of now, I think everything is displayed on my part. I see no issues with this. I think what happened, if I got the question correctly, is that it's possible to hide the cell clicking on the side usually, or even sometimes here, I think. So you can do show hide code, but it should be possible to see the code actually, because I made sure that anyone with the link can see this code. So I'm not hiding. But it's possible that maybe it got hidden by these kind of commands. Same time it may happen. So what I wanted to show again is the dashboard where you can see the current temperature of the QPU and also other interesting parameters. Having said this, what I would like to try to do now is to get the token. Okay, so again, here we have two different set of users probably today. So those of you who registered to the event with a Polito mail can try running the Lagrange client script that we installed before. Okay, so essentially, once you run the script, what you get is an URL. You have to click on this URL. And when you click on this, what you'll see is this kind of authentication page. Okay. Please disregard the fields in which is asking you to put the username and the password. And what you need to do is to use the Polito single sign-on option. Okay, so this one here. You click on this, and it will automatically redirect you to the login page of Politecnico, and you can use your usual credential. Okay. So this is the first thing for those of you that have Polito credentials. If you don't have Polito credentials, don't run this cell, or if you run it, please then stop this, because otherwise this keeps waiting for you to log in. Okay. So you click on this only if you are able to properly do the login. In this case, I already did the login. So I just grant access to IQM client. And what happens is that if I do so, I get the access token, which is this object. And the access token actually is also saved as a JSON file, okay, on the environment provided by Colab. But again, if you don't have Polito credentials, don't run this or stop this from if you already started running it, because otherwise you cannot go. Okay. no. Was anyone successful in logging with the credential of QubiTO? Yeah? Okay, that's good. That's cool. If you were successful, again, you should see here a token that is different in principle from this one, but is your own token. And it's the validity of the token is 7 days, but actually you are all added to a specific project on our dashboard that we show you later that expired today. But if you're interested in keep using the quantum computer, contact us. We'll see what we can do. And essentially, once you did the login, what you need to do is to load in a local variable or an environment variable your token. And this cell is quite useful because if you save the token, actually the script automatically saves the token for you. So if you were successful in running the script and do the login with the Politecnico credentials, you should see a tokens.json file here, clicking on this folder. And is taking that file and extrapolating the token from that, and you are good to go. But even if you cannot run that cell because you don't have Politecnico credential or you did not use Politecnico credential to register for the event, you can still run this cell and it will automatically instantiate the access token variable with my token, essentially, okay? So you will still be able to run the quantum circuit on the quantum computer. However, you won't be able to access the online platform to retrieve information on your job. You can just look at your job and the information provided by the results in the Python notebook. For those of you with a Politecnico account, they will have this extra feature that I will show later. Okay, so now we have the token. Let's connect to our quantum computer. To connect to the quantum computer, of course, we use the library we installed, Qiskit IQM, and we import an object called IQM provider, class called IQM provider. And to connect to the machine, we need to provide the address of the machine, which is hosted at this URL. So spark.quantum.linksfoundation.com/station. And of course, the access token. So we are telling it which quantum computer we want to use, the one hosted at this URL, which is the one hosted here at Politecnico. And of course, the access token to make sure that we have the possibility to access the quantum computer. Okay? Then you can create what's called a backend instance. So essentially, this Lagrange backend is the quantum computer itself. To obtain Lagrange backend, we just need to do provider.getBackend. Okay? By the way, you can ignore the warning that probably I will get, but is safe to ignore in this case. Yeah, ancora? No problem. Oh, yes, sorry, I didn't run this. So please remember to run all the cells. Again, you can ignore this warning. This is just complaining about some version of some libraries that are required for inner workings of the platform, but no problem at all. And then we established a connection with the quantum computer. Now what we need to do is prepare our quantum circuit that we defined above to run on the quantum computer. The first step is to transpile our quantum circuit. What does it mean to transpile a quantum circuit? Well, it means, again, that we are working at different level of abstraction. So me, as a quantum programmer, I want to work at the level of gates and, let's say, measurements and a higher level of abstraction. But the quantum computer understands the language of microwave pulses. So there needs to be a translation between these two levels. So this is analogous in some way to the classical compilation step in classical computing. However, is something a little bit different. So we don't call it compilation, but usually we call it transpilation. We are transpiling the circuit in order to be understandable by our specific quantum computer. How can we do this? There is a function in Qiskit that is called transpile, and the function needs two things. It needs the circuit we want to run, so our Bell circuit that we created above, and it needs the quantum computer on which we want to run it. So in this case, the quantum computer is the Lagrange backend. Once you have transpiled the circuit, just for sake of simplicity, I call the transpiled version of the circuit T-Bell. We can execute the circuit on the quantum computer using the method .run of our Lagrange backend. Okay? So Lagrange backend .run, and providing the circuit, the transpiled circuit as parameter, and also the amount of shots, so the amount of times we want to repeat the experiment, because I remind you, we need to repeat the experiment multiple times to reconstruct the output distribution. We can indeed execute the circuit, which means that if I run these, I send a job to the quantum machine. It will get queued in a queue. Usually the queue is, let's say you don't have to wait a long time in the queue. However, tonight there are many of you here, and also from home, so it's possible that you will need to wait a little bit before the job completes. But still, I hope it's not a lot. And essentially, after the job has completed its execution, well, even before it has completed the execution, you can get some information about the job, like the ID, the unique identifier of the job, and we'll see how this can be useful later. But also, you can get the result of the job, and this will wait for the job to finish, of course. Finally, these results, of course, are what we call the counts. So the raw results are telling you how many times I measured 0, 0, how many times I measured 1, 1, how many times I measured 0, 1, or 1, 0. So all the possibilities using 2 qubits that I can observe, that I could observe. However, in this case, to have an improved visualization, I'm using this plot histogram function to plot these counts, these results, as an histogram. Okay. Again, if something is not clear from my explanation, each line of this cell is explained below. Okay. So for each thing, you have what is doing, etc., etc. So now, if you're ready, I think we can try this. And it should work. Okay, so first thing is printing the unique identifier of the job. Again, this will be useful later. Secondly, is now waiting in the queue for the job to complete its execution. So before starting this session, this was almost instantaneous, but of course, I suspect that many of you were faster than me, and so you already sent your job to the machine, so we are now waiting for the result to come back. And please notice that for this session, the machine is reserved only for the people in this room and for the people connected from home. So we have the possibility to do what are called reservation, and we are telling the machine only accepts jobs that are sent from people with a Politecnico account that are registered for this event, or people using my token. As you see, the job completed its execution, and we get interesting results. Because if you remember, we executed this circuit 1,024 times, and we expect from the theory, since this is a Bell state, to only observe states in which the 2 qubits are both 0 or both 1. Indeed, we can say that most of the times we observe 0, 0 or 1, 1. So most of the time, the result satisfies what we expect from the theory, okay? So we are indeed observing experimentally a Bell state that we prepared using Qiskit, okay? We are observing the results of a Bell state measurement. However, there are a non-zero amount of times, specifically 29 for 0, 1 and 26 for 1, 0. Of course, the result may be different for you. We are not running the same job. but you should still see some amount of shots that are observed 0, 1 or 1, 0. And these are not expected because I constructed the circuit in a way in which if I observe the first qubit being 0, the second one should be 0. If I observe the first qubit bit 1, the second one should be 1. Why I still see 0, 1, 1, 0? Well, because the quantum computer is not an ideal machine, it's a proper real quantum computer. If I was simulating the quantum computer, I could obtain perfect results, but still I'm using a proper real quantum computer. It's normal that due to the effect of noise, I got errors during my computation. And so in some limited amount of cases, I observe results that are not consistent with what I would expect, okay? This is very important because current quantum computers, not only the one here in Politecnico, but any quantum computer in the world, is currently in the NISQ state, okay? So noisy intermediate scale quantum era, which means that these are not fault-tolerant quantum computers. These are quantum computers that are sensitive to noise. And so the computation, especially a complex computation, can be corrupted by noise. This is very important because our field of study also includes way and approaches to mitigate or correct the errors coming from this noise, okay? Of course, the end goal, the holy grail, would be to have a fault-tolerant quantum computer, and on the hardware side of things, people are working very hard towards that objective. Now, one of the last things I want to show you, well, first thing, maybe if you want more details about the transpilation process, this is a link actually that allow you to visit a page where you get more information about the transpilation process, because in the time we have, I cannot go too much into details. However, what I can do is show you the platform on which those of you that have a Polito account can also retrieve information about the job they sent and they executed. Specifically, if you click here, and you again allow Colab to redirect you to the website, if it's asking you to log out, that's normal. You click log out, and then you can log in again. Okay, with your credential, like this. Rightly so, two-factor authentication, why not? Okay. You reach, sorry, this was not aim. You reach the platform, and on the platform, what you want to see is maybe not everything I have here, because I have an admin account, so I see maybe more items on the left than you. But what you for sure should see is this tab jobs. Okay. On this tab, you can see all your jobs, and you can retrieve the jobs by looking at the job ID. Okay. So the job ID that we printed, essentially, sorry, here. Okay, so this one, you can find it also here. For me, it will be difficult because I'm not the only one using this token to run jobs, but all of you are using this token to run jobs. So I have many, but somewhere here, there will be also the one that I'm looking at here. In fact, I think is, no, it's not this. I can try to find it. But this is good because it means that a lot of people are were successful actually in sending job to the machine. Let's say somewhere there, you will see the ID of the job. And with that, you can check the results, not only from the Python notebook, but even from the machine, okay? So for example, if I click on the result link, I have a lot of information regarding the timeline of my circuit execution. So for example, how long it took to execute the circuit on the quantum computer. Okay, I can check this and check how many seconds it required to run the circuit. But also, I can check the results that I get looking at these, so the counts that I mentioned before, but also I can get even more information. For example, if I look at the calibration report, I can check the exact parameters of the machine in the moment I executed the circuit. And I wanted to mention this because this is a level of granularity that you cannot have if you don't own a quantum computer. So IBM, Google, the other providers of quantum computers that offer you access to the cloud won't allow you to access this kind of low-level details. But especially for research purposes, it's crucial sometimes to being able to access this kind of information. So essentially, what you can do with our quantum computer is also see under the hood what's happening. Okay, and if you want to try, if you have a Polito account, you can. Okay, so another thing you can do is, let's say we have up to 7 o'clock, 7 p.m. Okay, so if you want, what you can do is try also to modify the circuit we executed. For example, I told you that the Hadamard gate put the qubit in a uniform superposition of the two states 0 and 1, which means I expect the qubit on which I apply an Hadamard gate to be measured half of the time 0, half of the time 1. But you don't have to trust me. You can check this by yourself. If you, instead of a 2-qubit quantum circuit, you create a 1-qubit quantum circuit, and let's say you just apply the Hadamard gate without applying the CNOT, you get a circuit with a single qubit and the Hadamard gate. There is a question.
Qua, se non randono questa cella con access token, non possono rendere neanche questo, però tu gli passi access token. Ok? Vedi?
Come?
Tu guardi sul 40. Scusa.
There was one thing that was not extremely clear in my explanation. Apologies. But people with a Polito account still need to run. Let me make sure that this is clear. Still need to run this cell. Okay. No matter what is your credentials or your account, you still need to run this cell. This cell works both from people with a Polito credential and for people without Polito credential. Because what this is doing is, if you have Polito credential and you run this cell above, you got the token. Okay, the token is in a file called tokens.json. Okay, in the environment of Colab. So you have the file, but still this cell is required because this is reading that file and putting the string token inside this access token variable. So people from Polito still needs this part, okay? It's just that they will have the token.json file, okay? People that are not from Polito or that didn't register with Polito credentials, they will still need to run this cell, but the flow will follow this other line of code, okay? So still you have access token, but now in the access token, you have essentially my token. Is this clear? Yeah, there might be someone with Polito account that maybe registered a bit late, and so we were not able to add the emails to the project related to this. If you are not able to get the token, even if you have the Polito credentials, please run this cell to get the predefined token that I hard-coded in the notebook. Okay. Yeah, there is also this possibility. So what I wanted to show again is that I can change the circuit. Now is a single qubit circuit with another Hadamard gate. So I would expect half of the time to measure 0, half of the time to measure 1, and I can check if this works. Okay. So essentially, I can do this is already done, so I don't need to rerun this. I just need to rerun this part. Now I'm sending another job. I'm in the queue with all of you, so I'm waiting now for my turn on the quantum computer. And once it finishes, I can check if indeed the results are the ones I expect. This is the ID. Again, useful because on the platform, I can check, and now I see it because I was fast enough. So this is the same ID that I have here. Also, is it? No, someone was even faster than me, so this is already other jobs that are being sent, but that's completely fine. But however, I have the results. Again, I theoretically expect to measure exactly half of the time 0, half of the time 1, but we are not in the realm of ideal theory. In practice, I see approximately half of the time 0, half of the time 1. Okay. Still here, I also have errors. Okay, even if both outputs are expected, it's not that I don't have errors in this case. Is that, of course, errors are masked because both states are plausible states. Okay. How many of you were able to run at least one circuit? Okay. Okay. Good number, I would say. You can also check if you want to see your jobs. Actually, this is quite cool. You can also go to the project associated with the event. Okay, Quantum Days. And we can see the jobs that are being sent. And so you can see these are your profiles and also people with my profile that are sending jobs to the machine. These are the jobs currently in the queue. So they are submitted, but the execution did not finish yet. These are jobs that were already executed and you already have the results. Okay, and you can expect the result. And indeed, I see that a lot of people are sending jobs. One of the last things I wanted to say is, again, that if you check here, you see that this lot in the calendar of the machine, also if you click on dashboard, you should see this button, is reserved for you. So as I stated before, only you at the current time can run jobs on the quantum machine. However, we don't only provide access to this reservation mode to the quantum computer, but it's also possible to access the quantum computer with the queue system in slots that are not allocated to any specific project. So in this case, the slot that we are in currently is allocated to the project related to the event of the QubiTO Quantum Days. So again, is an exclusive reservation. But for example, next week, you see that there are some exclusive reservation, but also some cases in which the quantum computer is not reserved for a specific project. During those times, people with a profile and with access to the machine can still run jobs, but there is no specific priority. So it's a FIFO queue, first in, first out. So you send your job, you wait for the result. What I can guarantee you is that even at this time where we have tens of people running concurrently on the quantum computer, the queue times are way lower than what you would expect on a proper on a different quantum computer provided by bigger institutions like IBM and Google through the cloud. Okay. So essentially, another advantage of having in-house this quantum computer is that we can provide for students, for researchers, but also for companies that want to test and explore quantum computing access in a way that is faster and is also, let's say, wasting less time in the queue for them because of this. Because these machines are very limited in numbers. So, for example, IQM sold, I think, 12 quantum computers around the world. So there are 12 quantum computers like this one in the whole world. IBM has others. Quera is starting to sell some machines, but still you can, let's say, sum up all these quantum computers, and probably the ones that are openly accessible by the public are in the order of tens, maybe 100, but still not more. Okay, and more people are starting to explore this. So in principle, more access is always good. Are there any questions? Of course, if you want, yeah. Yeah.
Hi, can you hear me? Okay.
Yeah.
So we were also at the presentation for the quantum computer with the IQM head chief, whatever.
Yeah.
And surprisingly, there was a lot of skepticism about actually implementing, using and working with the computer, with the quantum computer on a daily basis. And my question is it possible to, at the current state with the limited hardware we have, to run simulations now in a more efficient way or in a faster way? On what are the advantages as of right now? Like, is it worth it now, or?
You mean using the quantum computer instead of classical computing?
Basically, yeah, like in my research, in my work, is it worth it now, or should we wait?
Thank you for the question. It's a good question, very interesting one. So the idea is that, again, we are in this era of noisy machines, okay? So not properly fault-tolerant quantum computer, which, to provide you with a clear example, these are quantum computers that are not able to run Shor's algorithm at large scales, okay? Shor's algorithm would for sure provide you with an advantage that is very significant, and you cannot reproduce it with classical computing, with anything else than quantum, okay? And in that case, I would say, for example, if your work is to break cryptography, for sure you want a quantum computer, but you want a fault-tolerant quantum computer, okay? So the idea is that as of now, we don't have yet fault-tolerant quantum computers. So it's not that these are useful for day-to-day tasks, except day-by-day tasks, except maybe for very, very, very specific instances of application of random number generation. But even in those cases, you have dedicated hardware. So it's not probably the best solution to have a quantum computer. For most people, this is something that has to be seen as a research tool, as an exploration tool. So to explore the potential to research solution to the current engineering problems related to quantum computing, but is not something that we'll use on a daily basis to solve tasks in mechanical engineering or chemical engineering.
Thank you. So you believe it's still important to educate people towards using it, both to help engineers solve the current problems and for the future?
Exactly.
Okay.
Exactly. I think it's important to start having quantum computing in the curricula because first we need the talented people like you to try and solve the problems that still are present in the marathon towards fault-tolerant quantum computing, but also because what is expected by analysts is that once the fault-tolerant quantum computer is present, is ready, is available, people and institutions that already invested in exploring and let's say educating the workforce to use quantum computers will have an advantage. So this is also why big institutions, we collaborate, for example, with Intesa San Paolo, but also Reale Mutua and many others, team. So they are investing on these, not huge amounts, but still they are investing because they want to be sure that if the technology one day is really maintaining the promise of being disruptive, they have people that have competencies on that technology. And we in Fondazione Links, we work a lot on this knowledge transfer because we want to, let's say, exploit the fact that we acquire this knowledge to transfer this knowledge to, again, researchers, students, and companies that are interested in being quantum ready, as they often say. Thank you for.
Is there any other question? Even at home, if you want, you can ask your questions.
Yeah. I think I answered this.
Okie dokie. So, yeah, sure.
It's because I missed the last lecture, and maybe I don't know, maybe just that it didn't figure out in any of the lectures. But I don't understand the control not operator. So you say that first of all we get our zeroth qubit, that's in our zeroth state, and then we apply the Hadamard operator, and we put it in a undefined state between 0 and 1. And then you say that if this the zeroth qubit is in the zeroth state, if it's in the first state, in the state 1, we flip the other qubit.
Yeah.
But doesn't the fact of knowing if the first state, the zeroth qubit is in the state 0 or 1, mean that we have to have measured it?
Yeah, that's true.
And when we have measured it, doesn't it collapse back to the first state or the zeroth state?
Yeah, that's true. That's an excellent question because it's not intuitive at all. But the fact is that we don't know. We do not know the state of the qubit after the application of the Hadamard gate. And we don't need to know the state in order to perform the control not gate. Let's say the control not gate is performed whatever the state of the control qubit, okay? The fact is that to explain the behavior of the CNOT gate is simple to do this explanation of saying, okay, now we don't know the state of but let's say it's 0. If it's 0, we are doing nothing on the bottom qubit. Let's say it's 1. If it's 1, we are applying the operation. But this is not, what happens in reality is that the gate creates entanglement. And so the resulting effect is this one. So they are both 0 or they are both 1. But again, to explain it in a logical and coherent manner, we use this language. However, it's not like we know that the top qubit is 0. We know after the measurement, okay? So if you want afterwards, we know, let's say we know that we measure the top qubit is 0. So we know that the CNOT gate did not apply the NOT port on the bottom qubit, okay? If at the end of the circuit we measure and the top qubit is 1, we know that the CNOT gate applied. But it's not like that we need to know for the CNOT to work. It's all, let's say, part of the computation. We observe always at the end, or usually, very often at the end of the computation, okay, we measure, and we can, even if you want to reconstruct what happened, but what happened still follow the rules described by the gates, okay? Yeah, but that's right.
Thank you. All right, we have... Okay, we have a question from home.
Yeah, please.
You can type in your question if you want.
Yes, let me just. Okay.
I can read it, maybe. Yeah. So you said currently companies are investing on talent, but on global scale, how much of a viable career in general quantum computing is?
Yeah, I would say, since you put global scale in your question, I would say is probably a viable career. Because in Italy, what I said about not much is true for Italy. In other countries, they are investing a lot. For example, in the States, but also in China, but also in Japan, but also in Australia, they are investing billions on quantum computing. And billions are, let's say, the total made up of government investment, but also companies that are investing. And let's say that abroad, you have also a plethora of startups. For example, let's say the company that sold us the quantum computer, so IQM, was theoretically, still is a startup born in Finland, but actually I think it's raised something like hundreds of millions in the last funding round, and they are hiring a lot. So I would say if you are not afraid of looking also outside Italy, it's for sure an interesting career. And the advantage of this career is that you acquire, in doing this, a set of skills, a set of, say, a knowledge baggage that is quite multidisciplinary, okay? So no matter your background, actually. So if you are from, for example, you are a mathematician, or you're, let's say you did physics engineering, or computer engineering, or computer science, etc. There is place for you in quantum computing. And if you are from one of these fields doing research in quantum computing, you will acquire knowledge that pertain also to the other fields. This is not unique to quantum computing, of course, but in quantum computing is especially true. And so I would say it's a viable career at the moment internationally. In Italy, maybe the things are a bit different because, let's say, we are not only on quantum computing, but on many other things, we are a bit slower to catch up. So investment, there are investments, but still on a smaller scale.
All right, we have more than plenty of time for another question. Okay.
But if there are no other questions, maybe what I can do is provide still in the last couple of minutes some details about the quantum computer itself. Because what I did not mention, because I was afraid of not having enough time, is that there are several technologies, several possibilities to implement the qubit. So the quantum bit, the fundamental unit of information in quantum computing, okay? In our case, our quantum computer is a superconducting quantum computer. So the qubits are Josephson junction that need to work in a regime of superconductivity. This is also why we need extreme temperatures to make our quantum computer operate correctly. But there are other options. And maybe it's good that I briefly mention to you that, for example, another option to implement the qubit are neutral atoms, but also trapped ions, but also photons, and in other case, even other physical apparatus that you can use to represent the qubit. Essentially, you need a physical system with two well-separated energy levels that, of course, will map to the 0 and 1 state, okay? So if you think about a specific kind of atoms, or in our case, the Josephson junction, this is possible indeed, but is not clear at the current, as of today, let's say, is not clear which will be, if it will be only one, the winning technology. So each of these technological approach for implementing the qubit has advantages and disadvantages. In our case, for example, we are able to perform a lot of shots, so repeat the experiment a lot of times in a very brief period. And we also have a very mature technology, also from a production standpoint. In fact, the quantum computers that are sold to institutions like ours are usually, most of the time, superconducting quantum computers. However, for example, a technology like neutral atoms is slower in performing the shots, so the samples related to the experiments, but, just to say one thing, allow a better connectivity between the qubits. Because in our computer, we can directly put in entanglement or directly interact with using two qubit gates only with the gates that are near each other on the chip, on the physical chip. We can still do two qubit operation on qubits that are not one next to the other on the chip, but we need to use an intermediate qubit as a bridge. And this entails an overhead in terms of operations. Neutral atoms, they use very, very, very cool laser scissors, something like tweezers, laser tweezers, that they use to manipulate individual atoms. And so they are able to arrange them in configurations that allow this higher degree of connectivity. Actually, neutral atoms qubit have all-to-all connectivity. So just to say that there are not only superconducting qubits like the one of the Lagrange machine, but you have many other technologies that can be used to implement a quantum computer.
Okay, I think we have one last question,
yeah,
or it might be the last.
Okay, so I don't know actually if this question makes really much sense, but I was wondering if like the C naught could be implied for more than 2 qubits. Like if you could make a C naught with 3 qubits, and that would imply, I guess, a multiple entanglement. And I was saying before that I don't know if that makes sense, because I always heard that the entanglement works just with 2 particles, and I don't know if theoretically it makes sense with 3 qubits or more.
No, yeah, thank you for the question. It makes absolutely sense. And you can entangle indeed more than 2 particles. This you need, if you want, at least 2 particles to have entanglement, but you can have entanglement between more than 2 particles. This is possible, okay? And indeed, you can have, let's say, a generalization of the C naught, which we call multi-controlled NOT gate, which indeed does what you described. So, for example, it applies the NOT gate on a certain qubit if and only if more than 1 qubits, a certain amount of qubits, are in the one state, okay? And the thing is that, again, on an higher level, these gates exist and you can implement, actually, it's very simple. If you, instead of CX, write MCX, and you can pass a list for the, actually, you can even see how this works. You can pass a sequence of indexes for the control qubits. And so higher level, this is quite simple. Of course, lower level, this means that you need to implement this object on the quantum computer. And the way you do this is using multiple CNOT gates. So even if I do this, and now you see maybe that is looking like is performed in a single instant of time in the quantum circuit, actually you need multiple sub-operation to implement it on the quantum computer. But still, you can do this, and it is indeed possible, and you can have entanglement between more than two particles, for sure, in theory.
Okay, I heard that there might be a question from the last row. Okay.
I'm curious about whether it's possible with the system to create a superposition that creates the state 1 with a given probability A, let's say like a parameter we can set like 5%, 10%, 20%. Is there a way to create a structure that we can just input a number and that it will create that percentage of 1 happening?
Yeah, good question. You can do so. However, in principle, let's say it would work and it makes sense if you have just a few qubits and you want to do that. We do that all the time. So you are not strictly required to prepare a specific probability distribution. You can prepare whatever you want. Please keep in mind that increasing the amount of qubit linearly, you are increasing exponentially the amount of states you can measure in output, okay? Because each time, essentially, you add 1 qubit, you are doubling the amount of configuration in output that you, for example, if you have 1 qubit, you can only observe 0, 1. If you have 2 qubits, you can observe 0, 0, 1, 0, 1, 1, 0, 1, 1, okay? So again, the amount of qubit grows linearly, the amount of possible output sequences grows exponentially. If you want to, for some reason, load for each of those possibilities, possible output state, a specific probability, you can do that, but this is not efficient because it grows exponentially with number of qubits. So let's say you have a circuit with 50, 100 qubits, that is already very, very complex because you need to, for each probability, load that specific coefficient for that specific state. And you have 2 to the 100 possibilities, okay? 2 to 100 possibilities. So this is indeed not feasible at large scales. What we do usually is we use gates like the Hadamard gate or etc. to put, for example, all the qubits in a uniform superposition, which means that we are not specifying each individual probability, but we are saying we want to observe in output any of these states with equal probability. So it's a uniform distribution, if you want. Okay. You can also load different distribution of probabilities, but in principle, it's not efficient to load a different probability for each of these states, because the amount of states, the space containing all the states, it's called the Hilbert space, is growing exponentially. Okay, but you can do that.
Okay. So I think we can wrap this up.
Yeah.
Okay.
Thank you.
So thank you very much,
Thank you,
Dr. D, for the occasion that you gave all the attendees to use this, to use the quantum computer. I must say the first time I used it was pretty magical. So I hope you felt like this, all of you. Please one round of applause for Dr. Dri. Okay. I'm a bit saddened by this time. I wish it never came, but my dear Leonardo, we have to wrap this event up. So what can I say? Thank you all for your attention, and thank you all also for those who followed at home during all these days. I remind you that the Lagrange quantum computer is public for the show. If you want to take a good look at it, you can find it going at the end of the even rooms aisle up to room 12. Then you go to the left and go towards La Dispe laboratory, towards room 14, and you find it on the right with His Majesty. I mean, it's very cool. You go take a look at it. And as last words, I want to say that if you didn't get any sticker, please come to me. I'll give you one. So you can have these neatly printed stickers, and go follow QubiTO on their social media. And if you have anything, any information that you want to know, please reach out to all of us. And thank you again.
I just wanted to add that I think we are really glad to have organized this event, and these were the first time for us, and I think there will be some follow-ups, like some other events similar to this one, maybe some talks. So check on our page and on our social, and we will give some news. So thank you again for coming. We are really happy about the excitement and participation. So have a good evening.